Okay, good evening, dear students. Last class we discussed about the different statements of second law of thermodynamics and spontaneous process with example and definition of non-spontaneous process with example. In today's class, I am going to discuss about the important 6 marks question, that is a Carnot cycle. The unit name is Thermodynamics 2. Thermodynamics 2. Here, Carnot cycle. Carnot cycle. Here, the cycle means it is a cyclic process. Carnot cycle means it is a cyclic process. Cyclic process means here when a system completes a series of changes and ultimately returns their original position is called as a cyclic process. It comes in a original state. You takes a cycle and the changes is completes here. It completes a series of changes and ultimately returns their original state is called as a cyclic process. And here the entire process changes is known as a cyclic process here. The entire changes, the entire changes is known as cyclic process. Is known as a cyclic process. Here, the entire changes is known as a cyclic process. And here, the internal energy of a system, the present system, you know what is meant by system. And here, the entire the internal energy of a system depends only upon its state, and it follows that in a cyclic process that net change of internal energy is zero. Therefore, internal energy is zero and work, the heat transferred and work is done is equals to zero. Work done is is equal. Heat is equals to the work done of a system. Here, it is delta E is equals to 0. Then delta U is equals to Q minus W. Here this is delta E is equals to 0 and 0 is equals to Q minus W. Therefore, this is Q is equals to W. This is a heat and this is a work. When heat is transferred to the system, this is work is done equal to heat here. This is a work is done here. This is a Carnot cycle. Therefore, Q is equals to W. And here the Carnot cycle graph. This is a graph, and here this is A, P1, V1, pressure is P1, volume is P1, and this is B, this point is B, P2, V2, and this is C, and this is D here, and here C, D, P3, V3, and this is D, P4, V4. And here this is T2 temperature and this is T1 temperature. This is T2 and this is T1 temperature. Here this is a isothermal expansion. This is isothermal expansion. This is adiabatic expansion, and here the adiabatic compression. This is a isothermal expansion, and here the isothermal compression, and here isothermal compression. Adiabatic compression, and here adiabatic expansion. Isothermal compression, and here adiabatic compression. Adiabatic compression. Here adiabatic expansion. This one here. This one isothermal expansion. It is transferring to this. And here adiabatic expansion. Here this is transferring in this to this here. And here this is isothermal compression. It is transferred this to this. And here the adiabatic compression transferring this to this. And finally comes or returns their original state. This is known as a cyclic process. That is a Carnot cycle. Here, this is a adiabatic expansion. This is a P. Here, this point is A, B, C, D, and A is a P1, V1, B is a P2, V2, C is P3, V3, and D is P4, V4, and this here in upper it is a isothermal expansion, isothermal compression, adiabatic expansion here. There are 4 processes here. The entire process is changes offered as a cyclic process. This is the entire process is changes and it gets original process. This entire process is referred as the cyclic process. This is the Carnot cycle, or it is also known as a cyclic process, and it is a imaginary and theoretical. The most well-known cyclic process is a Carnot cycle. Here this is imaginary. Another, it is a theoretically. It is the most common example for this cyclic process is a Carnot cycle. Here there are 4 processes. One is a in Carnot cycle consists of 4 processes. Carnot cycle consists of Carnot cycle consists of First one, isothermal process. Isothermal process. Second one, adiabatic. Sorry, you're right. Isothermal expansion. Isothermal expansion. Second one, this one, adiabatic expansion. Adiabatic expansion. Third one, isothermal compression. Isothermal compression. And fourth one, adiabatic compression. And these are the four processes. One is isothermal. Remember these four important processes. It completes these four processes are completes the Carnot cycle process. Or it is a cyclic process. Here one is the isothermal expansion. You come from this to this and this to this and this to this and this to this original state here. One is isothermal expansion, second one is the adiabatic expansion, third one is the isothermal compression, fourth one is the adiabatic compression. Here it plays a significant role in the solution of thermal system. It takes place a significant role in the solution of a thermal system. The cycle is employed to demonstrate the maximum convertibility of a heat. Here you are converting the maximum convertibility of the heat into a work. Here the conversion takes place heat into a work. Here the work is Q is equals to W. This is conversion takes place. The heat is equals to W. Heat into a work is conversion takes place in this Carnot cycle. In this process, we consider the perfect monochromatic light. Here, gas. The monochromatic gas. Here, gas is that is pressure. You want pressure here. P1, P2, P3, and P4 here. It consists monochromatic gas and in a cylinder fitted with a frictionless and weightless piston. Here it is connected with a frictionless and weightless piston. The gas is then subjected to a series of four successive steps. Successive steps. Those are these four successive steps: expansion, isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. First one, isothermal expansion. Back here, first one, isothermal, this one, isothermal expansion. Isothermal expansion. Here, first in the isothermal expansion, this place is this area undergo isothermal expansion. You know this is A to B. A to B temperature is T2. Here B to C temperature is T1. That is a isothermal compression. The temperature is T1, and here the isothermal expansion, the temperature is T2 here, and the pressure, and here pressure is P1, P2, and volume is V1 and V2 here. The cylinder is placed on the source and the piston here. The cylinder is placed in the source and the piston is then allowed to rise slowly. The gas is now allowed to expand isothermal. The gas is allowed in a expanded isothermal and the temperature is T2 here. Gas is explained here, expanded under the isothermal, and here the temperature is T2, and so the volume is increases from V1 to V2 here. This is a temperature. When it is allowed in an expanded isothermal process, the temperature is T2 and volume is increases from here to here, that is V1 to V2. Here the volume is increases, that is V1 to V2, and in an isothermal process, dou E, that is the energy, the dou E will be 0, that means I already written here Q is equals to W, that is delta E will be 0. That means from the first law of thermodynamics here, the first law of thermodynamics is delta E is equals to, right here, delta E is equals to Q minus W. Here that is internal energy is 0. Delta E is equals to 0, and this 0 I will substitute in this, and here 0 is equals to Q minus W, therefore is equals to Q is equals to W. How much heat is transferred, that much work is done in this isothermal expansion. And here, so heat is absorbed. Here heat is absorbed is equals to the work done by the system on the surrounding. It is here the heat is absorbed. This is equal to the work is done by the system on the surrounding. This shows the first law of thermodynamics in a isothermal expansion. And here let QAB here. This is a QAB, take capital QAB, and the heat absorbed by the system at the temperature T2. Here QAB is the heat absorbed by the system and temperature is T2. This one temperature is T2, and WAB is the work heat absorbed, and WAB is here. QAB. You take QAB and WAB. It is a heat absorbed and work done by the system on the surrounding. And then QAB is equals to the WAB. Therefore, WAB is equals to PD. This is a PD. Right? This is a integration of this. WAB is integrated of PdV. PdV means here the limits are V1 to V2. It increases, that is V1 to V2, and P is the, that is a gas constant. PV is equals to RT here. This is V1 to V2, and therefore PV is equals to RT here in this equation. Here you know the temperature is P here. The temperature is P, and here you know the temperature is T2. You substitute in place of T is a T2 here. Therefore WAB is equals to integration of V1 V2. P means substitute here RT2. P means substitute here RT2 RT2 by V into D. Therefore, this you take outside this RT2, it is constant here. WAB is equals to RT2 integration of V1 to V2 into 1 by P into dV. Therefore, this is equals to RT2, that is 1 by V is equals to V, and V1 to V2, that is dV. So we get 1 by V means log V. Here log V, you substitute V1 and V2. First is upper limit and second is lower limit. You substitute upper and lower. WAB is equals to RT2. WAB is equals to RT2 log of V. Limits are V2 by V1, and here AB is equals to RT2. Here log of V2 minus log of V1. Finally, you take the log of V2 by V1. And right here, log of V2 by RT2 log of V2 by V1. Therefore, this is QAB. This I will continue write this one. You take the logarithmic form, you know logarithmic formula. When it is a subtraction, you take in a division. QAB, this is equals to WAB. Therefore, this is equals to RT2 log of V2 by V1. Okay, this is a isothermal expansion formula. Therefore, this is equation number 1. Get equation number 1 here. This is equation number 1. In here, the gas cylinder allowed here in the expanded in isothermally, the temperature is T2 and volume is increases. That T1 V1 is equals to P2 V2, volume increases, that is volume is the limits are V1 to V2, and here V1 according to first law of thermodynamics. Here delta is the energy is 0 here, this is equals to 0, and its first law of thermodynamics, 0 is equals to Q minus W, Q is equals to W, how much and heat is absorbed, the work is done on the system for surrounding here, and QAB you take in this here points A and B, and this is equals to WAB, that is the work is done, and then this WAB is equals to P into dV, integration of P into dV. And here limits are taken V1 to V2, and you know the gas constant, that is PV is equals to RT, and here P is equals to RT divided by V, and this value substitute in this P value. And here the temperature, you know here T2 temperature, and substitute here T2, and when it comes D and C, you substitute the temperature is T1, and here R is equals to T2 divided R T2 divided by V, and here the integration of R T2 divided by dV, and log of 1 by V, that is integration of 1 by V dV is equals to R T2 log of V V2 V1. And then apply the limits V1 and V2, and here WAB is equals to R into log of V2 minus log of V1. Finally, you get the equation, that is QAB is equals to WAB is equals to R into log of V2 by V1. This is a isothermal expansion. Next, second one, this AB, next BC. AB, next BC. In this, we know formula is QVB is equals to WAB. So this is equals to RT2 log of V2 by V1. This is the first one. Second one, isothermal expansion is completed. Second one is adiabatic expansion. Here you get a negative value. This get a negative minus W B adiabatic 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 expansion. Okay. Adiabatic expansion, here also the first law of thermodynamics, delta E is equals to Q minus W, and here you get a D minus W. The work is done less here. Minus W. Here the cylinder is not taken out of the source. Here the cylinder, here this place is cylinder, and here the cylinder is taken out of the source and completely insulated. The gas is then allowed to expand here. The completely insulated and gas is expanded adiabatically from the volume is V2 3 V2. Here you get a limit is V2 to V2. The volume is V2 to V3, and the work has been done by the system adiabatically when it is not in a position of to absorb heat. The temperature of the system fall from T2 to T1. Here the temperature is from the T2, and as Q is now becomes 0 here. So again from the first law of thermodynamics, this heat is absorbed, that is Q is 0 and the work is done here minus W here, that is according to first law of thermodynamics, delta is equals to 0 and here the Q is equals to 0. You get Q is heat is 0 and here the Q is equals to 0. You get Q is heat is not in a position, only you are in not in a position, only you are in a range here T2 to T1 or T1 or here T2 to T1 you get a negative value, therefore that is a delta E. T is equals to 0, delta E is equals to Q minus W, therefore delta E is equals to, that is minus W. Here this is a 0 minus W, therefore it get a minus W value, that is energy minus W. That is adiabatic expansion. From the definition of heat capacity, for using heat capacity, that is the CV is equals to delta E by delta T. According to heat capacity, CV is equals to delta E by delta T. Heat capacity, CV is equals to delta E divided by delta. This is of heat, and here delta CV is equals to delta E by delta T. This is of heat, and you multiply CV into the delta T is equals delta E is equals to, you get here the delta E is equals to CV into delta T. CV into delta T, the range is here T2 to T1. This is T2 to T1. Therefore, delta E is negative. We get W is equals to minus CV into T2 minus T1. Here delta is equals to CV is equals to CV T2 minus T1. This one T2 to transfer in here T1. T2 to T1 here. This is delta is equals to CV delta T2 minus T1. Here the delta E value is that is a minus W. Therefore here minus W is equals to this one minus W is equals to CV into D2 minus T1. This is the equation for that is W DC. That is W DC. Then you take T1 minus T2, T1 minus T2, it get a positive value, that is W is equals to CV into T2 minus T1. So this is a second, and next third one, the isothermal, this one convection. Third one, isothermal compression. Isothermal compression. Here the isothermal compression insulation is removed. Here you are inserted in insulated, and after this isothermal compression the insulation is removed and the cylinder is transferred to the source reservoir at the temperature is T1. Here the particular temperature is T1, and the gas is then compressed isothermally. Here the gas is expanded isothermally. Here gas is compressed isothermally, and here the volume changes from the V3 to V4. Here this volume changes V3, this one to this one V4. Here volume changes V1 to V2, and here volume changes V3 to V4 in a compression quantity of heat that is C and D. Here you write that is Q C D Q C D W C D. That is the work is done here. And here the work is done WD. The gas by the fission temperature remains constant, that is T1 temperature remains constant, that is T1, but in this process the sign of the QCD and WCD will be opposite of the QAB and QWAB. QAB and WAB. QAB is a positive, that is WAB is this, those are equivalent, Q and is equals to AB. That is opposite, and this sign is opposite to this one. Positive, and these two are get negative value. And here I will write the isothermal compression is same. Thermal compression is same for same procedure. Only you are changing V3 and V4, and same here, that is a P into D. You write here W. You get only here is equals to WCD. Therefore, this is V4 by V3 to V4. You take the lower limit is V3 and upper limit is V4. Here, but I will write directly here. Therefore, WCD, therefore is equals to RT1 log of V4 by V. You take same here, that is WCD, therefore is equals to integration of V3 V4 T into T. Take same here, P is of RT, so PV is equals to RT and V P RT by V, and here substitute RT1, here the P1 is substitute, and afterwards then finally you get this equation. Okay, next one, that is last one, adiabatic combination. Fourth one, adiabatic combination. Here the adiabatic combination, in this, here W is equals to, this is W is equals to this BC, W is equals to BC, that is the CV into T2 minus T1, and this is equation 2, this is equation 1, and here this is equation. Finally, here the fourth adiabatic compression is equation number 4. The adiabatic compression, in this case, that is the adiabatic compression, is considered D and E. Here we consider this curve, that is a D and A. The gas cylinder is removed from the hot reservoir and the cylinder is once again insulated. Here the cylinder is insulated and here cylinder is insulated, here cylinder is insulated. Here expanded and here expanded. It removes the insulated or this capital expanded, that is isothermally. Here it is insulated adiabatically and here insulated adiabatically, and is once again that is insulated here, and the gas then compressed adiabatically T2. You get the temperature is T1 to T2, the volume is changes V1 to V4, and the system is restored its original state. This whole system is, this changes and then it changes and then it changes and then it goes to the original state and restore the original state. The work done will be WDA. This one is the WDA work done, WDA, and the gas is given, that is QDA is equals to 0, that is Q heat is 0. Here also heat is 0. Here this is heat is 0 minus W is work done. Minus W work done is I get here minus WDA, that is QDA. This is equals to 0 minus W. This is get up minus W, that is delta E is equals to minus W dA, and here from the difference of heat capacity, same here the heat capacity, here this is a CV T2 minus T1, here you get the delta is equals to minus W dA, and here the heat capacity is CV delta E. CV is equals to delta E divided by delta T into V, and here you get CV delta T is equals to delta E, and here you get the T1 minus T2. That is, therefore this is equals to CV delta T is equals to delta. Therefore this is that CV is equals to this one, therefore is equals to CV into T1 minus T2. Therefore this is equals to delta. This you get the fourth equation number 4. That here remove the minus W. Then you substitute the delta E value is minus WA. Minus WDA, here minus WDA is equals to the CV into T1 minus T2. here. Therefore, this delta E is the minus WdA. Therefore, this is equals to the CV into T1 minus T2. This is equation number 4. This is equation number 4 for the adiabatic compression. This is a adiabatic compression. That is equation number 4 here. Finally, the total net work done by the gas on the completion of the cycle. Here it is total work done in isothermal. Sum of the isothermal, it get a positive value, and adiabatic isothermal expansion get positive value, and adiabatic expansion get positive, and next isothermal compression get negative, and subtract, and adiabatic compression is get a negative subtracted. It is a finally written as, I will write here the complete equation. The total work done by the total work done the total work done by the gas on the completion, by the gas on the completion, by the gas on the completion of the cycle, the gas completion of this cycle is given by therefore W is equals to WAB plus WBC minus WCD minus WDB. Or you write first in the general, that is W is equals to WAB plus WBC plus WCD plus WDB. You get in your equation in a corner cycle. Here W is equals to WAB plus WBC, and WCD is negative, and WDA is negative. This is a overall sum of this one. Total work done on the completion of the cycle is given as this one. W is equals to WAB plus WBC minus WCD minus WD. Okay, I will stop here only. Next class, add this formula. First we get, that is a RT2, and you do homework. This is you simplify this equation, that is WAB. You know the formula is RT2 log of V2 by V1 plus CV T2 minus T1 minus this one RT1 log of V4 by V3 and plus another WDA is, that is CV into T1 minus T2. You get the final equation is, that is QAB minus QCD. The net work is done by the system is RT2 log, final equation RT2 log of V2 by V1 minus RT1 log of V4 by V3. That is, you get a equation number 5. You do homework for this. Thank you.